So in this video, we are going to talk about that automorphism of S6 that is not inner. And it turns out one of the constructions I know of actually involves S5. But in the process, it's kind of fun to look at S5 and its subgroups while we're at it anyhow. So usually in an undergraduate modern algebra course, as I mentioned before, they sometimes point out that A4 has no subgroup of order 6. And it's worth pointing out the corresponding fact for S5. This is unrelated to the proof that we're going to do. I just mentioned it because I noticed this. And it involves CELO theory techniques. So it's worth pointing out how you can use CELO theory to prove stuff like this. The claim is S5 has no subgroup of order 40. And so how would you prove such a thing? Well, suppose it did. By CELO theory, H has a CELO 2 subgroup and a CELO 5 subgroup. We're working with H specifically, and 40 is 2 cubed times 5, and so the number of CELO 5 subgroups in H has to be congruent to 1 mod 5, and it has to be a divisor of 8. So you see it has to be 1, which means that whatever the subgroup of size 5 is, it is normal. But we're working with a permutation group, S5. So in particular, P is going to be a 5 cycle, generated by a 5 cycle. Up to conjugating our subgroup of order H, we can actually assume that we're talking about 1, 2, 3, 4, 5. Let's make our lives easier. Likewise, H has a CELO 2 subgroup. Let's call it Q. And it has order 8. So you're looking at a subgroup of S5 of order 8. Worth pointing out, Q also has to be a CELO 2 subgroup in S5, because 8 is the largest power of 2 dividing 5 factorial. And so in particular, all these subgroups of order 8 in S5 are conjugate by the second CELO theorem, so they're all essentially the same. I wonder what that group could be. Well, it's worth pointing out the same story is true with 4 factorial, right? The largest divisor of 4 factorial is also 8. So this tells you that there's an order 8 subgroup in S4. And in fact, we all probably already know what it is. One example is a dihedral group on 8 vertices. As generated by the permutations 1, 2, 3, 4, and 1, 2, 3, 4. Why does that matter here? Well, by the CELO theorem, 8 is the largest power of 2 dividing 4 factorial, so by the CELO theorems, all subgroups of order 8 in S4 are conjugate to this one. S4 is a subgroup of S5. Each of these CELO subgroups, D8, is thus a subgroup of S5 of order 8. They're all conjugate. All the subgroups look like dihedral groups. So the punchline is H contains a dihedral group of a square, and it contains a 5 cycle. In particular, for our group of order 40, we have this 5 cycle, which up to conjugation, we're assuming we're working with this 5 cycle. And we've got a dihedral group of order 4, and particularly we have these permutations. More importantly, we have at least these two. Well, let's look at the powers of this cycle. You also have 1, 3, 5, 2, 4. 1, 4, 2, 5, 3. And of course 1, 5, 4, 3, 2. And so the point I'm getting at is, if you conjugate by this permutation, let's call it tau, by my 5 cycle, let's call it sigma, you're going to stay in H. But you're going to have swapped two of these elements in their positions. So let's assume for a moment that 1 is fixed. Then you're going to swap 3 and 2, and 4 and 5, or vice versa. So you're going to either end up with 1, 3, 2, 5, 4, if you're talking about the permutation that swaps 2 and 3, 4 and 5. But you might not be talking about that permutation. Other possible choices might have swapped 2 and 4 and 3 and 5. So this would have been case A here. This would be case B. What would you get there? You would get 1, 2 and 4 switch places. 3 and 5 switch places. And then the last one, case C, you'd have 2 and 5. 3 and 4, in which case you'd have 1, 2 and 5, 3 and 4. So you see, in case A and B, you end up conjugating and getting a 5 cycle that's not an H. Because remember, H has to have a unique subgroup of size 5. So all the 5 cycles have to be these 4. And so once you get these two cases, we have a contradiction. Of course, here I'm assuming you fix 1 without loss of generality. Of course, cycle through so that the first element in the 5 cycle we have is the one that's fixed. By this argument, you see that what has to happen is that the only permutation that doesn't cause a problem here is the product of 2 cycles with the feature that the element right before 1 and that the 2 and the 5 swap and the 3 and the 4 swap. I'll just state it that way. So permutation like this. If it's a different fixed point, you can figure out what you need to swap 2 and 5 with. You replace them with this. You put the fixed point up front, and you replace 2 and 5 with the sigma of that fixed point and sigma inverse of the fixed point, and vice versa. But I'm sure you could see what the other problem could be. In that case, we still have our other cycle to work with. Our 4 cycle, in that case, would be 2, 3, 4, 5, which we'll call pi. Now what happens when you conjugate by pi? Well, 2, 3, 4, 5 all switch places. Somehow that's supposed to be an H, and yet it's not one of our 4 allowable 5 cycles. So the point we've seen is that H must have a normal subgroup of order 5, and so it must have these 4 or 5 cycles, and it must have a subgroup of order 8, and we've determined that must be a dihedral group. And now just by conjugating, we end up with 5 cycles that are not in H. But H has to be closed under multiplication. So the only way out is one of our assumptions must be wrong. clearly the Silo theorem is not the one that's wrong, so the assumption that must be wrong is that there's a subgroup of order 40. You can check that it turns out that's the only divisor of 120 that gives you a problem. As you can tell, this type of argument relies more on just Silo theory. It usually relies on knowing a lot of the other subgroups in the group you're already studying. In this case, we already have to know about the subgroup structure of S4 in order to be able to get this dihedral group argument working. And this subgroup structure about 5 cycles. And it's those two things together, along with the Silo theorems we use to get this contradiction. Okay, now with that little appetizer out of the way, it is worth pointing out that if we look at S5 itself, and we look at the number of Silo 5 subgroups, according to Silo theory, the possible answers is either 1 or 6. Of course, it's not too hard to see that the answer must be 6 because, well, each subgroup of order 5 is generated by a 5 cycle, and the number of 5 cycles is 24, which is 6 times 4. So they're naturally grouped into 6 different subgroups. Alright, so there are 6 subgroups. We'll let S be the set of Silo 5 subgroups. Note then that S5 acts on S by conjugation. And by the Silo theorems, this action is transitive. What do I mean by that? One of the theorems is that any 2 Silo 5 subgroups must be conjugate. Therefore, given any 2 elements in S, there must be a permutation such that when you conjugate one Silo 5 subgroup by that permutation, you get the other. So congratulations, you must be able to get everywhere. That's going to pop up in a moment. But more importantly, because you have an action, you therefore have a homomorphism from S5 into S6. Why? Because S has size 6. And you can check that this homomorphism is injective. Because what's the kernel of the action? Well, you would need a permutation with the property that it fixes all of these. And remember, P is going to be the cyclic group generated by a 5 cycle. And we've already seen that when you conjugate a 5 cycle, you're going to get another 5 cycle in a particular way. And in particular, the only way you're going to get something in the same subgroup is if and only if sigma itself was in that subgroup. And so in particular, the only way this works for a given P is if sigma is in that P. So if we want that to be true for all P, we're going to need a sigma that's in the intersection of all these CELO 5 subgroups, which means we need something that's a power of all these 5 cycles. The only one that's going to work is the identity permutation. So you're injective. And you're transitive, which means you now have a transitive permutation group. So the upshot so far is if we define H to be the image of S5 under this map, it is a subgroup of S6 of order 120, and it's a transitive permutation group. Which of course is supposed to mean for any x in the set 1 through 6, and any y, there exists a sigma in this group with sigma x equals y. In particular, there's no element, no global fixed point. Because if you have a global fixed point, then you can't be transitive because there's no way to get to x from any other y. How is this useful? Well, then S6 acts on the coset space by left multiplication. This gives rise to another homomorphism, which I'll call pi. It goes from S6 to S6. So coset actions are also transitive. And so what would the kernel be here? Well, you're looking at permutations with the property that sigma times tau h equals tau h for all tau. But of course, sigma tau h is equal to tau h if and only if tau inverse sigma tau is an h. Or more accurately, you can just use the fact that this is supposed to be the intersection of sigma h sigma inverse. Overall permutations. That's something you can prove, and it's one of the homework exercises in the book I didn't assign. For arbitrary group actions, something like this is true. So we need to claim that this is trivial. I'll assume that for now, for the sake of proceeding with the argument. If that's true, then this is injective, and because these two groups have the same size, it means it's surjective, and hence an isomorphism, and hence an automorphism. Of course, here you might recognize I'm kind of cheating because these two 6s aren't representing the same set. This 6 is representing this set of cosets. And this 6 is just representing the integers 1 through 6 originally. And the reason why I point that out is because we now have this automorphism from S6 to S6. And if I look at H under this left subgroup, remember this is coming from this group action. What happens when you do left multiplication on this coset space? Well, you fix the cosets. In particular, under this action, H is in the stabilizer subgroup. For this corresponding action. And so assume, of course, S6 mod H, it's got a bunch of cosets. Namely 6 cosets. Let's choose them, of course, so that sigma 1 corresponds to the identity. And so these 1, 2, 3, 4, 5, 6 corresponds to the 1, 2, 3, 4, 5, 6 over here. And the point I'm making is if I let this group action be the correct one I'm working with, then here, when I'm talking about stabilizers, to say here that I'm talking about H is a subset of S6, and that this statement is true, I'm saying that the corresponding permutation must be sending pi of H to the stabilizer. In particular, it's another version of the symmetric group, namely S5. Here being viewed as permutations of the cosets sigma 2H through sigma 6H. So the point is, for every element of H, it permutes these latter 5 cosets but fixes the first one. And so under the group action and under this corresponding bijection, every element of H maps to a permutation that permutes these cosets but fixes the first one. So whatever its cycle type is going to have H as a fixed point and then stuff. In particular, it can be viewed as an element of S5. So all that's to say is that pi of S6 is equal to S5 as a permutation group. Note here the point of emphasis. I'm not talking about abstract isomorphism. I'm talking about quite literally, we have a fixed point of every permutation in this set, the same fixed point. Why does that matter? Well, because the claim is that pi is not an inner automorphism. That this is an example of a non-trivial automorphism. And one way to see that is if you had a automorphism that is inner, you can check and see that what it does to subgroups is it sends them to conjugates. And so if pi were inner, then we would have a problem. So if pi were equal to sigma g for some g, then pi of h is just a conjugate of h, which would still be transitive. You can check that the conjugate of a transitive permutation group is still a transitive permutation group. That's a bit of a problem because what we just noticed was that pi of h has a fixed point. Or what you might call a global fixed point for the subgroup. Namely that pi of h fixes the coset h. So pi of h is not transitive. because there's no way to map sigma 2 of H to H. And so, oops, you can't be an inner automorphism. Therefore, you now have the property that pi is an outer automorphism. So that's one way of constructing this automorphism using only CELO theory type stuff. It's not the only way. I know of at least three other constructions. One involves working with an isomorphism with a general linear group. Another one involves working with alternating groups instead and looking at the symmetry group of the icosahedron. And then the third automorphism I know way of constructing this automorphism is completely combinatorial. But I like this approach because it involves only stuff from CELO theory and group actions to get the job done. An interesting fact that's also harder to prove is that this automorphism still sends the alternating group to the alternating group. Oh, I should be using A6 here. Because in general, you can prove that the automorphism group of the alternating group is always the automorphism group of Sn. Although in general, that's pretty hard to do. The other reason I like this strange construction is it gives an example of an automorphism group that sends one subgroup to another where it isn't given by conjugation. Namely, we had two different isomorphic copies of S5. One's this kind of weird one that's actually a transitive subgroup, and we constructed an automorphism that sends this transitive one to one of the ordinary S5s we're used to. Of course, there is one gap in this proof. We still have to figure out the kernel of pi. Well, one cheating way to figure out is to note that it has to be a normal subgroup of S6, and then you just point out, and something you would have to prove is that the only possibilities are either A1, the alternating group, or the whole group. And that's not too hard to prove, because if you had a normal subgroup in S6, by one of the isomorphism theorems, intersecting it with A6 would have to give you a normal subgroup in A6. But A6 is simple, as we just proved, which would tell you that either n is equal to A6 or n intersect A6 is the trivial group. Or I should say more accurately, n intersect A6 equals A6. But you know, if n contains half the permutations, then it's either going to be half the permutations or the whole group. So that's not that interesting. In this case, you're saying that n avoids half the permutations. And so in this case, I mean, what other choices could you possibly have? By one of the theorems about direct products, you now have two normal subgroups, n and A6, whose intersection is trivial. Then that would mean that the set NA6 is an isomorphic to the direct product of n times A6. And yet somehow is also a subgroup of S6. That kind of forces the size of n to be 2. And you can prove that there's no normal subgroup in S6 of size 2 directly, because that would mean you have an automorphism, and yeah, automorphisms aren't closed under conjugation, so you have a bit of a problem there. So congratulations, these are your three options. This is order 720, this is order 360. Note that this kernel also has to be a subgroup of H, which has order 120. Congratulations, it must be trivial. So I did this argument separately, but it's also worth doing because it gives a good application of some of the isomorphism theorems from previous algebra courses. And one of the advantages of using simple groups. If you know information about being simple, you can use it to bootstrap to prove theorems about normal subgroups, or which subgroups are normal in a larger group.